Okay, got a vector A where I gave you the components. A vector B has magnitude 5 and the x component's -3. You know, I always recommend a sketch. Okay, 2i plus 3j would be maybe here. This is 2. This is 3. Magnitude of b is 5 and the x component of b is -3. It means you go over here at -3, then you draw an arrow of length 5. You might not be sure exactly where to draw that, but it's going to be quite a bit longer than this one. So, and the arrow has to have a projection down to here. Now, that might be an accurate picture and it might not. But at least you got something to look at and something to work on, okay? So here's your vector B. And we know that the magnitude is 5. So what can we do with this? Well, we can figure out the angle and magnitude of A, right? But that's not really going to help us add A and B. We've already got the components, which is what we generally want to have to add two vectors. So it'd be great if we could get both components of B. Well, it's fairly easy to do. First of all, we draw a triangle with 5 here and 3 here. We ask ourselves, what's this? Because of course, right here, whatever number we have is going to be the y component of your B vector. Okay, so 5, 3, well, this is going to be the square root of 5 squared minus 3 squared, which is 4. I gave you a nice 3, 4, 5 triangle. Okay, so last time I'll be nice to you in this, unless it's an accident. Okay, you're not going to try to make them all come out nice and even, but a lot of times they will. Okay, so we know that this side is going to have a magnitude of 4. We have some ambiguity here. Okay, this could be the vector B. But the vector B could also be this. There's 5. One component could be -1. We don't know. Okay. So we got to work it out for both. So magnitude of BY equals 4 from this triangle. BY is close to -4. Meaning that B equals -3i plus 4j or -3i minus 4j. There's a subtlety there, and you got to be aware of possibility that you have two possible solutions of that. Okay. Quadratic formula gives you two solutions, right? Often, kind of a majority of the time, it turns out when you're doing motion, you can discard one of them. Okay, but you got to document that you can discard one. Here, there's no reason to discard anything. Now, if I'd have told you that BY is positive or BY is negative, then you'd know which one it is. And from this context, your syntax of whatever problem this might arise in, you probably know. If you don't know, you got to do it. I wouldn't even penalize this. If you did everything right on this assumption, or even this assumption, you didn't do the other one today, by grading this really strictly, it's still there by. Okay, you got to be aware that sometimes though you have to deal with two possibilities. Now, if B equals -3i plus 4j, then A plus B equals 2i 3j minus 3i plus 4j. Now you know that you can add the i's and add the j's, but the algebra is compelling. This and this are like terms because they're both multiples of I. This and this are like terms because they're both multiples of j, right? So just a slight extension of simple algebra and simplification tells you that this is 2i minus 3i plus 3j plus 4j, which equals negative I plus 7j. Okay. Now that all comes out in the picture. I mean, we can write these I and j vectors. Here's 2i, and here's 3j. And over here is, I have a good sense today, but anyway, this is negative 3i. This is 4j. So this vector is 2i plus 3j. You put the vectors here, head to tail, draw the vector so you can put it head to tail, and you get this vector. You draw this vector head to tail with this one, you go from here to here, you get this vector. You want that picture, you want that idea, and you want to know that the algebra works. Okay? Everything agrees. Everything is completely consistent. Mathematics is consistent at this point. Okay, now I didn't ask for anything other than a plus b, but we could say a little more. We can say the magnitude of a is the square root of negative 1 squared plus 7 squared, which is the square root of 50, which is 5 times the square root of 2. And the angle, which I'll just implicitly call theta, the inverse tangent of the y component and I don't want equals there because the inverse tangent gives me an angle in the fourth quadrant. You got to know that you do the inverse tangent, and then we're probably working in degrees at this point, plus 180 degrees. This is because x is negative, meaning that you're certainly not in the fourth quadrant. You can also be in the second quadrant and get that ratio. Okay? You need to understand that deeply and kind of not forget it. And at this point, well, you go to approximations on your calculator. It's this again, 7. Maybe that's 173. One more thing we can do. Another part of the picture. And a little more board space to do it. I'm going to rob it from the original problem. So I've got 2i plus 3j plus negative 3i plus 4j. Make sense? From here to here is my vector. In terms of the components. And it's very clear if I go 2i That's 2 units to the right, 3i, negative 3i brings me back to negative I and all that stuff. You want to also see that picture. You should start sketching these things to reinforce it. They're simple pictures. Once you've done it a few times, you've got it. But do it a few times until you're sure you've got it. Okay. Because then you have pictures that help check your work. If you're an engineer, you want to check your work 2 or 3 different ways. You really don't want to have your, whatever it is you're engineering, fail. Okay. And good habits. Now, I'm not an engineer. Your engineering instructor, Mr. Hale, can tell you a lot more about what an engineer has to do. But I think he's going to tell he's pretty consistent with what I'm saying. And if it isn't, feel free to ignore me. You're going to be an engineer. Okay. Take his word over mine. Okay. As I said, I never wanted to be an engineer. I wanted to be a theoretician. Around midlife, about 10 years ago, I was in my 30s. Yeah, you just laugh uproariously at that. I started to realize that my engineering is pretty cool. I was supposed to go to a reunion last week. There were going to be about 60 of my fraternity brothers there, and about half of them were engineers. The other half started in engineering, went into sales or whatever. Okay. Bunch of people couldn't go. My wife came down with COVID Friday. Actually, she got diagnosed. She'd had it for a week. She's not that sick. Running a little mild fever. Some days she feels fine. Some days she's a little off. Those are the days when I want to get out of the house. No, not really. Those days when I really want to be around, but she's fine. Yeah, very disappointing. I couldn't go. I mean, it's been 5 years since the last one. We might never have another one. A lot of people I would have liked to come out because I do get feedback on what engineers do. And one of my closest friends is like RCA's Engineer of the Year once. RCA is like whatever the big electronics thing is now. Just connect with those guys, seeing how they think. Gives me some insight. Shows me what I missed, and that's all right. Would have been neat to do it all. Okay. I do have some insights into engineering. I went to an engineering school. Engineering, math, physics. Okay. This problem. Going to be to your benefit if you understand what I'm doing here. Let's see there. Now you understand what I did here. It's just distributive law. This times all this times all this expands out the way it does. Okay. Okay, now basically, our rules for I and J and K is going to have K also get into 3 dimensions. So I and J are in the plane, K goes this way. Now, basic principle dot product is 2 vectors are perpendicular, dot product 0. If they're parallel, their dot product is just a product of their magnitudes. Okay. So you can write this as a kind of a formal mathematical system. It's a very simple one. If you apply that principle, I, J, and K are all mutually perpendicular. So I dot I has to be 1 and I dot either of the other two, since it's perpendicular, 0. Overkill to write all this out. I'm going to do it anyhow. Those are the rules. Got a question, so I must want something done. Let's see. Okay, at this point, somebody raise their hand, quoted the definition of dot product that you got from your book, and it's absolutely right. You're about to see why it's right. It comes from these rules. So now if you'll just write out 36 times whatever this is, 8 times whatever this is, 54 times whatever this is, and 12 times whatever this is. And be careful, I'm going to make sure my J's really look like J's. Big old hook on them. Okay. The whole point is, yeah, you've got a simple rule for this thing, okay? I component times I component, J component times J, and all that. Okay, that's fine. But there's a reason for the rule, and you'll understand it more deeply, and you'll understand what things mean better. If you understand that we can expand this by the distributive law, just simple distributive law. And once we've written out what we get, and I wrote it up here, which so as not to have a lot of confusion on the race. That one can keep the big one here. Now, if you know the principle, if they're perpendicular, they give you 0. And if they're parallel, it's the product of their magnitudes, right? And of course, they're unit vectors. Everyone has magnitude 1. So I dot I, product of the magnitude of I, is the magnitude of I, they're parallel. I is parallel to itself, it's got magnitude 1. I dot I is 1. Now I prefer you write that 36 times 1. Okay, write it out clearly and neatly, like I don't always. And see how you get from here to here. And I dot J, well, I is perpendicular to J, so that's 8 times 0. J dot I is 0 because it's perpendicular. J dot, the two are perpendicular. J is parallel to itself, its magnitude is 1. So J dot J is 1. Write it out explicitly. It's the first time you've seen it like this. Don't skip steps. Write it out so you go back in your notes and look at it. If you forget. I think it's pointless. Likely in this course, if you really understand it, you'll find that it isn't. And when you get to multivariable calculus and do all this with the cross product and try to understand the cross product. And of course, we got to do that in this course too, second semester. And cross product does occur this semester. It was in your homework. Okay. It occurs when we get to angular momentum, which is very much related to what goes on with that rotating beam. Okay. So you break this down. If you break it down for the cross product and the rules for the cross product, which are equally simple, except you gotta use your right hand. You might know what I mean, and you might not. You might have seen it, you might not. Actually, maybe you saw it in homework. It's gonna be easier to understand. So we're building in something here. I don't do anything pointlessly most of the time. Sometimes I'll get off the whole digression. That's good for your soul too, but it might not make much difference in this course. Okay? So there we have it. Now, what do we do with that? Well, we can find the angle. So how do you find the angle? What do we know? V dot W is 48. We also know that P dot W equals what? It equals magnitude V, magnitude W, times the cosine of the angle between them. The angle between them is always between 0 and 180 degrees. Because if it goes around past 180 degrees, you measure the angle this way, just the angle between. Okay. You should know that because you did this in linear algebra, most of it. I think everybody in here has had linear algebra one time or another. Some of you, little, you know, been a little longer. Most of you just had it last spring. Okay, so this is something you should know from linear algebra. We're going to make sure we understand it and how we apply it to physics. Well, I'll skip a step here because I think everybody knows it. Okay. Now, we know V dot W. What's the magnitude of V and what's the magnitude of W? We don't know that yet. So we'll just calculate it up here. Magnitude of V is 4 square root of 13. Check my arithmetic. And it's wrong. No, it's 16 and 36. Okay. So 48 over 4 square root of 13 square root of 83. Question, hang on. Okay, we can approximate this. Square root of 83 is a little more than 9. Square root of 52 is like 2 times the square root of 25. Square root of 25 times the square root of 2. Okay, square root of 2 is about 1.4. 5 times that's 7. So that's like 7, and that's like 9. That'd be 63. It's a little more than 63. 48 over 64 would be 3/4. So I'm going to say maybe the inverse cosine of 0.72. It's pretty close to 45 degrees. Okay. Doesn't look like it ought to be 45 degrees, so maybe I did something wrong with my mental arithmetic here. It's not an uncommon phenomenon. I multiply 52 by 83, I get something a little over 400. Square root of 400 is 20. Well, no, 4,000. Square root of 4,000 is a little over 60. So get like 70. Maybe a little less at 72. Okay, so I'd say that's an overestimate. Maybe ought to be 0.63 or 0.65. Anyhow, it's not a bad idea to do estimates. So that you're kind of oriented toward the kind of numbers you expect to get. If I look at these two vectors, I say that angle's closer to 30 degrees than it is to 45. But that's a hand sketch. Okay. There's V, there's W. You project V on W by coming down here with the right angle. Okay. And your vector projection. And when I first asked, I just asked for the projection. You got a scalar projection, you got a vector projection, right? Scalar projection could be positive or negative. If V was back this way, you'd have to kind of extend the line of W and project down here. You know that. Okay. And your scalar projection would be negative. Scalar projection could be negative. Okay. Vector projection takes care of all of that. And it's pretty universally denoted projection sub W of the projection on W of the vector V. And well, this angle's theta. If it's a magnitude of V cosine theta, here's your hypotenuse, here's your adjacent side. This side is this side times the cosine of theta. And if that's not second nature to you, keep looking at right angle trigonometry. Okay? It's not totally obvious. Should be not. Or it should be by the time you come in here on Friday for sure. Because you're going to have to be able to do these just second nature. You don't want to be stumbling over which is a cosine, which is a sine, which side is the arctangent and all that stuff. Okay. The side isn't the arctangent, it's the angle. So I stumbled over it, be better than I am. Okay. And then the vector projection. You have to multiply the scalar projection by the unit vector in the direction of W. You know the projection's in the direction of W. You multiply a magnitude by a unit vector, and you get a vector in that direction, right? Oh, and the magnitude of the vector you get is just whatever you multiply. This thing's a unit vector. The projection is, well, step I should have done, so I'll do it over here. Okay, so what we have is magnitude of V cosine theta equals what? It equals V dot W over the magnitude of V. Why? Because V dot W is the magnitude of V magnitude of W cosine theta. You divide by the magnitude of W. And sometimes I'm using the double absolute value sign, sometimes the single, they mean the same thing. When I do this, I just kind of like to emphasize it's a magnitude. I think everybody understands that. And the magnitude of W divides out, and you get magnitude of V cosine theta. So this is completely obvious if you think about it a few times. This is just magnitude of V cosine theta. This is a unit vector. In the direction of W. I'm not going to write that out. I want to emphasize that. Okay. Now, what you used obscured all the geometry of it because you used the formula without thinking about it, so you don't remember it. And I'm not being critical, I'm just pointing out that's what people do. It's the short way to get the right answer, and that's your first goal, to get points. Okay. You think a little more deeply about it and understand why it is what it is. If you write this, it's yes. I don't like this formula because it obscures the geometry. It obscures the fact that you got this scalar projection here multiplied by a unit vector. And you forget that. And then you get later on to something where you really need to remember it, really need to understand it, and it's not there. Okay. So when you learn stuff, I mean, you've only got so much time. You do the best you can. Try to think back to where things come from. Take 30 seconds to think about it after you've solved a problem. What are the connections? If you keep doing that, you get more connections. And 30 seconds multiplied by a dozen times a day is 6 minutes. You do that much in a day, and you're going to get a deeper understanding. You're going to start to develop a deeper understanding, which will make a better, whatever you are, out of it. Okay. I think it'll make you into a better engineer. And it'll make you more successful in physics class and multivariable calculus, which is coming up, and differential equations, which you're taking right now. What are your basic principles? Where do you start? How do you move to the end? Okay. Instead of doing it just by habit, you have to start doing it by habit. Try to get beyond just here's the habit, here's the formula, here's what I use it. Okay, now I got to remember this formula. And now, oh my God, there's a test. I got 115 formulas to memorize. Okay. Try to convince you that there's maybe a better way. If you spend that 6 minutes a day, you might discover. Okay, just advice. Okay, so I raved for about 90 seconds, but try to boil everything. This is everything you need to know in this course about vectors. Except for one minor exception, we need the law of cosines second semester. Okay, that's something I assume you know, and we'll come back to you if you don't understand it right now. Try to understand everything in terms of just a few definitions. Definition of the sine and the cosine and the tangent. And the pictures that go along with them. Pictures of a right angle with 3 sides and the angle and all that stuff. And then understand how this, which leads to this. And if you got this picture, it's pretty easy to work this out. And if you're something that's in terms of the dot product. And of course, a picture of how the components add. All right. Come down, if you boil it down to that, if you understand how everything proceeds from those pictures or from those definitions, you're going to have a pretty good command of the trigonometry you need throughout most of your 2 semesters of physics. Take statics. If you're going to be a civil engineer, you're going to have to know it a whole lot better. You're going to have to know a lot more than you'd have to know for physics. Get this much down, make the rest of it much simpler. Now, speaking of lab, we observed this rotating wheel at different positions around a circle. And unfortunately, only 1/3 of the class ever submitted their data, so we can't do anything with it. Putting it on the record, I need it tonight. Okay. You're going to need to do more analysis on it. It's not difficult. Something that wouldn't take you 15 minutes to do right now. And then when you get the data, you do some analysis. And if you're the guy timing the pendulum, well, I can do a couple of extra things that aren't difficult. You can then share with everybody else. They can see a little bit more. Okay. Nothing I'm going to ask you to do is difficult except drawing conclusions, and that's challenging. Okay. can we really detect from the data that people were sitting around a circle? Okay. Was the data accurate and precise enough? That gets into a little bit of analysis of data, a little bit of statistics. Is that in my head or did something just beep? Well, I'm glad it was something. Unless it came from my head and you heard it, that's really bad. Okay, now, point is, we need to be doing a little bit of basic analysis of data. We're not going to do heavy statistics. You haven't had a course in statistics. We're going to do it kind of intuitively. We're going to do it with a little more than just a few vague rules that you get in your textbook. They aren't really very precise, but they're still a good start, okay? So that's where we're heading. Get that information to me by tonight so I can do something with it before tomorrow, okay? And I mean by, a lot of times I shut down around 7 p.m. If at all possible, get it to me before then, okay? Because the more data I have at, let's say, 5 p.m., the less I'm going to have to ask you to do. I'll do some of it if I have time, but I don't have to have it all. Okay. Best I can do for you in the 6 minutes we have left. Summarize what you should know about uniformly accelerated motion. And you remember a couple of the questions that I posed in class last time. Where would I put the ball on this ramp so that it gets to the end? Same time a ball in another position on another ramp with a different acceleration reaches the end. In case the two balls reach the end at the same time. That's kind of a capstone, not exactly a capstone problem, they're harder problems. That was kind of challenging, kind of be thinking about that. But your homework is going to have you learn, to develop more intuition about motion. There's some simulations and stuff. Get it done before Wednesday. Get it done. Okay. Because everybody is in striking distance, at least with the trigonometry. Make sure you strike by Friday. So what we know is, just in terms of linear acceleration, okay? Those are definitions of velocity and acceleration. A, V, and X are functions of t. You have 5 variables in the equations. Every equation has 4 variables. The 3 variables are known. Backward, capital E means there exists at least one, greater than 1, greater than or equal to 1. With those 3. There are only 4 variables in an equation. If there are 4 variables and you know 3 of them, you can solve for the one you don't know. Then you know 4 variables and you're home free. You just pick the equation that most easily gives you that 5th variable and you get all 5 of them and you've solved the uniform acceleration problem. That's where you are. Okay. Now you need a certain amount of intuition that we're trying to build. You know, things I told you to think about last time or suggested you think about 2 balls down the ramp, both get to the end at the same time, but the ramps have different slopes, release them both from rest where they have to be in order to get to the end at the same time. Or where do they have to be in order to get to the end with the same velocity? Okay, 2 different questions. You want to kind of keep those questions in mind. Okay, I don't have time to write it down. I've got less than a minute. There's your framework. The homework, I think, does a good job of developing an intuition with these quantities because nobody's really born with that intuition. Acceleration is kind of a mysterious thing to our caveman brains. We have caveman brains, which are pretty good brains. Okay. Equally good to ours, but they don't naturally grasp acceleration. Okay. Aristotle was smart as heck. Look at what he did. Pretty much from the ground up. Yeah, a lot of it was developed. He didn't get it. Newton. Okay. 1600 years later, you know, over 2,000 years later. I think, I don't remember when Aristotle was born, I was just small. I forget how old I was. Okay, the point is, it's a subtle concept. Make sure you give it full attention and develop as much intuition about it. Don't just learn to use the equations. You're going to come up short when you get a tough problem. Like the ones I mentioned, and even tougher. And then especially when you get into 2 dimensions, we have uniform acceleration this way, constant velocity this way. Then everything mixes up. Easy to keep straight if you know the equations. Hard to set up if you don't understand the concepts. Okay? Get the concept because the mathematics is really pretty simple. Be careful with dimension and units. It'll save you a lot of headaches.